Oh yeah, you know what you're talking about, right? So let me say it this way. Recursion for computer scientists is a recursive function. But I also want to talk today about recursion from a mathematical perspective, where it's just a mathematical function that has in its formula, right? It has itself on a smaller value. So recursion is not only an algorithm, it is also a mathematical function. So if we're talking about mathematical function, we can say it runs forever. But if we're talking about algorithm, it cannot run forever because we don't have infinite amount of resources. Usually it will run as long as the space in our stack gives, has some extra space for it to run, or there are some problems that, purge some of that. But if it occupies a whole stack, then it will crash. Last one. Oh. So this is more of a logical. The statement is written using logic rather than.
I'm not sure I finished my assignment.
Yeah. Oh, okay, I fixed it. So here's a statement. And what is f on input 5?
Yeah, we can play. I don't know.
We are doing the club.
It's bigger than 1, right?
Okay, so here, if we write it out in more pseudocode way, I would write it as follows: if n is smaller or equal to 1, then we return n. So it's okay. Return. Else, or otherwise, oh, you know what, let me use it, let me check. Otherwise, return n minus 1. You know that return terminates execution of any pseudocode. So if I hit this statement, I will not go to the next line. So what happens if I make a call for f on input 5? We come here, if n is smaller than 1, smaller or equal, then we return that value. This didn't happen, that's my stopping condition, and I come here and I return f on 4. But how does it look like? It goes here, I have another call for the same function, let's call it function on n. But my value becomes smaller. And then if I'm in this code with n equals 4, same exact logical flow happens because stopping condition is not true yet. I come here, I call f on value 3, and then next time I call it on 2, and then when I have a call for 1, that's the first time I actually hit my stopping condition, but I return n. And my n right now is 1, so 1 will be the number that is returned. And when 1 is returned to this function returns 1. and this function returns 1, and this function returns 1, and this function returns 1. So, so here's the correct answer is option 2. So I'll keep it running as a background for people who are late. But let us talk about formal definition of recursion. Okay, so recursion or recursive function is just the same exact function that has a calls on smaller instances of problem. They must get smaller and must have always a stopping condition. So notice also, it's not just enough to have stopping condition for recursion to stop. My problem should be getting smaller. If my problem is not getting smaller, if I make a call on f of n again or f2, and getting bigger, it will not stop, despite that you have stopping condition. Okay, so there are two things that actually must work together to stop your recursion. Stopping condition, obviously, but also your problem must be, must shrink in some way. So we have, in mathematics, we have two things that define recursion. Stopping condition is usually called basis step, and then we have recursive step. That's a recursive definition of a function. Here's an example from before. When we studied sequences, and we say, here's bacteria, we double amount of bacteria every hour, we would give explicit formula, but also here's another one that is a recursive definition of same exact sequence. In this definition, I have two things, basis step and then recursive step. So anytime you're dealing with recursive function, whether it's mathematical function or whether it's an algorithm, you must specify two things, basis and recursive step. So here's another example from before, Fibonacci numbers. Those, if you remember, are formed as, say, at index 1 and 2, I have ones, and then we add up numbers to get the next one. So we add up 1 plus 1 getting 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, and it's defined using the following the following formulas. My basis step here involves two things. You can say, why do I need this? What if I only keep, for example, f sub 1 equals to 1, and I completely just, push it away? What happens then? Yeah.
There's nothing to go behind the one, so like it doesn't really have, you don't have a two numbers to add one before and then one before that.
Yeah. So for example, on input, when I ask what is position 2, it says, oh, let me take a look at position 1 and position 0. Position 1 is a stopping condition, but position 0 says, oh, that's a recursive call. So what's at position 0? And then starts, and the infinite chain of recursive calls will start going on from there on. Okay, so if you have, like here, I do have two recursive calls in my function. I should be a little bit more careful because I need to stop propagation of this branch and propagation of this one. Okay, so your stopping conditions sometimes need to be a little bit elaborate. I know this example is very simple, but if you're working with recursive algorithms, it is a little bit more complex. It has different recursive calls on different sizes of the same problem. So you need to stop all of those. Let's do example. Say I have a function that is recursively defined as follows. My basis step or stopping condition is this, and here's my recursive step. So what is f on 1, 2, 3, and 4?
Who is that?
Well, if I'm to solve it consecutively for n starting at 1 and then getting bigger, that's easy job to do. I will just say, okay, f of 1 is, let's take this formula,
Take a screenshot. That's fine.
and instead of n, plug in 1 everywhere. Okay, then I say, okay, that's 2 times f on 0 plus 3. F of 0 is 3, plug it in, evaluate 9. So what's next one? I know it's 2 times 9 plus 3, 21. What's next one? 2 times 21 plus 3, 45. What's next one? 2 times 45 plus 3, and so on. But what I just explained was not a recursion. What I explained to you was an algorithm that uses an array and a for loop. Okay, what I just did was not a recursive solution of those things. Imagine you have 4 and starting at 1 to let's go to 5. And we simply evaluate those things and put them, say, at some array at corresponding index n, and then we iterate it. The for loop iterates it. We take it, so we say a at index n is 2 times a at index n minus 1
Wait.
plus 3.
Who is that? Oh, that's so cute.
Okay, so this is a for loop approach. Okay, then what if I'm actually interested to build a recursive function? I will have to do a slightly different thing, but in my slides, just before we go there, notice that this function defines a sequence, right? It's 3, 9, 21, 45, 93. It's just like a sequence. And the sequence can also be defined using a recursive definition. So notice recursive functions, they are like sequences. There is a lot of similarity between those two. Okay, now let's go back to our question. So imagine now I don't have my for loop, I don't have this, I don't have access to any of this information. It's gone. And somebody asked me, what's f of 3? I say, okay, let me take a recursive definition of this function, and that's this one. F of 3 is 2 times f of 2 plus 3. But I don't know what's f of 2. So I need to evaluate it. And I ask this formula again. So what's f of 2? They say, oh, it's just 2 times f of 1 plus 3. But I don't know what's f of 1. And I ask again and use the same formula again. And I didn't calculate anything yet. It's just my formula is getting bigger and bigger and bigger, and it all sits in computer memory, right? If you think about recursive algorithm. And this is the first place where I can actually get number back, not another recursive call. This is where my function stops. That's my basis. Here, that's my basis. And it's finally possible to evaluate this formula. So when I have the number, finally I can start doing things. Okay, so recursion, before we can do anything about it, it keeps on going in deeper and deeper and deeper and deeper, accumulating a lot of data that is stored before any evaluation ever happens. And when we hit this stopping condition and start climbing up from this chain of recursive calls, that's when we start evaluating things. Okay, so here I simply, this is my basis, and I can finally get the answer. Okay, so you will also be surprised to know that we have, I will say it this way, many of the things that you thought are, just a sequence or just a function or just this or just that, they can be defined using recursive definition. So for example, if you think about arithmetic progression, Mark, we also did book club, it's still running. Yep. So when you say arithmetic progression, you can define it recursively. So this is a explicit formula. What's at index n? But we can do it in a recursive way. So how do we do it? We need to define basis and a recursive step. And for this is quite simple for arithmetic because we know we started our initial term, this one, and then what is the value at index n? Well, that's what's as a previous one plus d, plus common difference. In a similar way for geometric progression, I can say recursively it is defined as follows. Basis is my first term, and then what's at position n? Well, let's look at the previous one and multiply it by r, common ratio. But there are other things. For example, factorial function. It is very common, by the way, on a job interview to hear things like, how about you implement a factorial function using recursion? How would you do this? Well, here's here's explanation. So you can represent it as basis and recursive step. For basis, that's your stopping condition. 1 factorial is 1. And for recursive step, well, we know that n factorial is just 1 times 2 times 3 times 4. And up to here, this product evaluates to n minus 1 factorial. So we can say, okay, you know what? N minus 1 factorial, that's recursive call if you are building factorial function. Well, that's recursive call on smaller input and represented this way.
vishalakaradarayak උනානේ මේක.
Okay, how about summations? I can even express summation recursively. I can create a recursive function that evaluates sum of, if I'm looking at some sequence, I'm summing up terms of this sequence recursively. What's my stopping condition? What's the basis then here? A sub 0 here. So we say, what's the first term of this sequence? And we look at our formula. Our summation starts at A sub 0. You can also, you have lower limit, upper limit. You can see, what's the range of your function. For recursive steps then, you can do the following thing. You can take sigma, that's your function of, this is f on input n. This is f on input n. So recursively, it will be expressed this way, f on input n minus 1 plus nth term. My upper limit here, n minus 1. Okay, so here you go. It's not so scary anymore. So don't get frustrated if a question like this comes up. You know what to do. Okay, let's do something that is a little bit more interesting. Let's say I have a sequence of numbers, and they are defined following the following explicit formula. at position n, I have numbers that is 9 to the power n plus 1. But I want to express or define this sequence using recursion. The beginning is easy. What's my basis? I want to define this function sequence recursively. Yep. Basis for basis. What's a basis step? Yes, 10. Oh, I thought you said n. Sorry, I misheard you. Yeah. So 10, right? Basis is 10. We can either explicitly just grab it from there, or we can use formula and plug in 1 instead of n and have it. Now, my recursive step, I need to somehow express a sub n in terms of previous terms. And this example will be simple because I will only be, I only need just previous step. In your assignment, you have one example where you will need previous and one before that to properly express recursive step for that. But let's do this one. Okay, so what's a sub n? Well, by formula, it's this one. I need to express this in terms of a sub n minus 1. Here's what n minus 1 looks like if I plug in this formula, right? 9 to the power n minus 1 plus 1. Here it is. I say that I can kind of reduce power here by taking multiplier 9 and put it in front of 9 to the power n minus 1 like as follows. Okay, I can do this. And I wish this number was 9. Right? Why do I want it to be 9? Because then, so I have 9 times 9 to n minus 1 plus, assume it's 9 times 1, then I can do the following. I can take 9 outside the parentheses and I have n, this plus 1, and this is a n minus 1. So I can then say, oh, it equals to 9 times a n minus 1. I wish it was 9, but it's not. So what do I do? By the way, we did ⴅ Can you communicate? We did ⴅ it's still running. So what can I do? I really wish this number was 9, but it's not. I can, help a little bit here. Remember our trick we used with summations? We can add a 0, right? But my 0 will look like plus 8 minus 8. This is a 0. But now I have my 9, that's what I wanted. And minus 8, it's like some extra stuff, but I'm fine with that. Okay, so let me rewrite this expression again. I have 9 times. We did ⴅ but it's still so now I have exactly what I wanted. I have this here, and then minus 8. Okay, I can now rewrite it explicitly. This is exactly previous term, and I have my recursive definition. So when you give your answer, you say, okay, this is my recursive step, and this is my basis. Two things, basis and recursive step. So in your assignment, there are several problems of this type, several parts, and when you have one of the expressions is a quadratic expression, it will require you to look at two previous terms to correctly define it. I might post some hints for that, but the trick is look at here, what I'm observing is really just I'm looking at difference between consecutive terms, but there you will also need to look at difference between differences between consecutive terms to get the idea. Or you can say, I would say, do this and then kind of do this again. Okay, you will get your formulas and then do this one more time to eliminate it, because you will have some reliance on n. Sorry, I'm maybe not explaining this well. So imagine you have this plus 3 times n. This is not clean. This is not a clean recursive definition. Okay, when you have n and reliance on the recursive call, this is not nice, because it's for loop and recursive call. Not good. So if you want to eliminate this one, you will at some point rely on even smaller call. Anyways, just try it. See if it doesn't work. I can post maybe some similar problem with a solution to help you out with that. Okay, let's talk about recursive algorithms. And here's two that quite simple. One is called H on input n. The other one is called M on input n. My stopping condition says if n is 0, just return 1. Otherwise, have a recursive call to the same algorithm with smaller input. Whatever it evaluates to, then multiply by 2 and return. So I have here one recursive call. In the other algorithm, which is very similar to this one, I have my stopping condition, same thing. But then instead of having a single recursive call and multiplying it by 2, I have two recursive calls to the same exact problem, right? n minus 1 and minus 1. I expect to get same answer, and then I will just add those together. So technically, H and M, they are solving the same exact problem. What are they solving? I give you n. What does this algorithm gives me back? Yep. 2 to the power n. Right. They're just calculating what's 2 to the power n. You give it n, like 5, it gives you, it's 2 to the, evaluates 2 to the 5 and gives you back. But they do it differently. Here I have one recursive call, here I have two recursive calls. They're both correct. They both solve your problem. Let's just see how it works. Okay, so when I say on small input 4, I call algorithm H. And imagine that this little block here, it's this code exactly just kind of copied and is sitting in your stack. So what happens there? I come here, stopping condition, n is 5, so it doesn't work. Then I come here, have a recursive call on 3, right? I have a recursive call on 3, and now I have another copy of the same code. Now I'm here in this code. Stopping condition didn't work. I come here 2 times, I don't know what value of this yet, because I have another recursive call to H and 2. Same copy of the code. Come here. I don't stop. Come here, another recursive call on H1. Again, come here, doesn't work, recursive call on H0. And in my H0, I have the same code. I come and n is indeed 0, so I hit return, and 1 goes back to the functions that called it. So now, and this function is gone from the stack. We freed up space. It's gone. It is terminated. We are done with it. But everything else here on the chain is sitting in computer's memory. When I'm here, I finally emerge. Imagine I'm emerging with number 1. This one emerges with number 1. I take that number 1, multiply it by 2, and return it to the function that called me. I'm here. To the function that called me here, I'm coming back to H2 with 2 in hand. In this code, I'm just kind of waking up that code. 2 is now sitting here. We multiply it by 2, return hits, and we return 4 to the functions that called us. Same here. Now 4 multiplied by 2, and we return 8 to the last code. Okay, now I'm in the very last code of this function. And I take this 8 multiplied by 2 and return it back to the user. Okay, whoever was first to call h on 4, here's your 16. Okay, so this is quite straightforward, works well. Now let's see a chain of recursive calls for m, and maybe try to visualize it for a second before I show you how it looks like. Take a moment and see how would m on 4 unfold as a bunch of recursive calls. How does it look like? Yep.
Like a tree?
It is a tree, right? So here it is. It's a lot of work. Notice that what happens here is that I'm doing a lot of repetition. Say here's m on 3 needs to get evaluated, but it then, despite that I already know what it is, I have to do it again because I have another recursive call for it. And m on 2, I have 4 of those, and this is a very small input. 4 is a small input. Imagine if you are asking what's m on 100. So this is a binary tree. How many levels do I have in this tree? It's a very tall tree. How many levels do I have here? Huh? 5, right, but in terms of m on input n, how many levels do I have?
N plus 1.
Yeah, n or n plus 1, right. We can say it's linear. There are lots of levels. So imagine that if I'm here at the bottom level, I have 2 to the power n just calls. So this is huge. Then we can say, what's about running time? Because both algorithms, they solve the same problem. They both correct, they both terminate. Everything is, sorry, yeah. 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 Yeah.
So how would this tree be?
Yeah. This whole, it's not like this whole tree will be sitting in the stack. I will show you how control sequence works, maybe on merge sort, but you know what, let me maybe do it right now for a second. In reality, imagine this is my control and things that I will store in stack. Somebody called m on 4. I have a copy of it, and when I come here to this code, I have recursive call for m on 3. So imagine I'm going here. This is control flow. So I don't have a chance to get there yet, because I will get there only after I'm done with the previous recursive call. Okay, I cannot get there right away. So the whole idea looks more like this. Imagine you are traversing this tree, and that's the first time you're coming from recursions, first time you're coming back. M on 1 will be the first function that will go past this plus. It will go here. Okay? M on 1 here will be the first function that will have second recursive call activated. And then it will evaluate this, and then we'll go, and this function will return. So then M on 2 will finally get a chance to have call here. And then it will go here. But this one, and this one, and this one, they will sit in computer's memory. So not the whole tree sitting in computer's memory all the time, right? And recursion doesn't work in layers, like all here, everyone here, okay? It technically goes following control flow, right? And functions are executed or called when their time comes in, right? So some of those will be in computer's memory, some of those will have already begun and expire, some of them will emerge later on. We didn't call them yet. Okay, so this is kind of a big difference. But in terms of efficiency, we still have to wait much longer in M function to go through all of this and give us answer compared to H function. So here I have comparison, number of recursive calls. I have n recursive calls in H, and 2 to the n here. Okay, I have only 2 to the n nodes at the bottom level, and 2 to n minus 1 before that. So there's lots of recursive calls. So when you think that you have, one recursive call and then another recursive call, it's not like it's twice more. It becomes exponential. So be very careful when you have when you build a recursive function. You can either, it's okay to have 2 recursive calls. I will show merge sort, and it has 2 recursive calls. There's nothing wrong if your design involves several recursive calls. It just how big is this tree? This one is very, very tall. Merge sort will have similar tree, but it will be very tiny, like really squat tree, tiny, tiny little tree. Same shape, but it will not go for a long time. So be mindful about this behavior, and what we see here, it's a curse of computer science. Making a little tiny mistake can really become result in a very slow algorithm. So notice here, when I built recursive Fibonacci, I have 2 recursive calls, and they seem to be different because I'm calling Fibonacci on n-1 and n-2, and they seem like different problems. You say, oh, but I'm not repeating same calculations. It looks like I'm not repeating the same stuff, but in fact you do. If you say Fibonacci on input 5, you can see that you do repeat same calculations. They're simply on different levels, right? And say, for example, here's Fibonacci 3, and here's again Fibonacci 3. So despite that in the code itself, it doesn't look like you are repeating things, well, you do. Okay? Recursion is kind of tricky to work with. Okay. And that's why runtime here becomes exponential. Efficiently, if you want to efficiently solve Fibonacci, you just use a for loop. Okay, no need any recursion. Okay, let's talk about merge sort. So merge sort is a recursive sorting algorithm. It is fast. It's very fast, and it's also fast compared to other fast sorting algorithms. It uses a very little number of comparisons. It's often the first choice when you when you're okay with extra space, because merge sort requires auxiliary array for its work. What does it mean? So if you're given, if you have like 1 million of items to sort, you give array of size 1 million to merge sort. To work properly, it will need extra array of size 1 million to do its job there. So you can expect that whatever amount of things you need to sort, you will have double of that space, right? Because merge sort requires auxiliary array. Unless your data are given as a linked list, then merge sort can go without extra array. It will be just juggling pointers, and that's fine. But very often the data is actually given as an array. Okay. Actually, I should say the scientists who we say developed merge sort, John von Neumann in 1945. Well, technically, there is another person, and nobody knows their name, nobody talks about them, but they used merge sort 7 years before this. They even had it patented. There is a document. It was used for sorting punch cards, and it was before John put his, published a paper with this algorithm. So it's possible that I'm making mistakes, but I think it's like this. So if you Google this person, they were before John published merge sort, 7 years before. Okay, so how does it work? So merge sort is a classical divide and conquer algorithm. So you give this algorithm array of size n to sort. The array is not sorted, there is no order in this data. So merge sort takes your array, it looks at it and it says, it's too big. This problem is too big. Let me cut it in half. And I will sort smaller array first, this one. And I sort this first, and then I will merge them together. So it looks at this array and says, it's too big, let's cut it in half. And it just simply, has a recursive column, smaller array, size n over 2 and size n over 2. So imagine I'm here, and that's merge sort on my first half of my array. And it looks at this array and it says, it's too big, let me cut it in half. And I will sort only quarter of it first and then the other one. So we split it again. And we split it again, and again, and again, and again, and again, until you have an array of size 1. So then merge sort says, oh, but this one is already sorted. How lucky, right? Look, array of size 1 is sorted. Array with 3, array of size 1 is also sorted. All of those arrays are nicely sorted. So so far we did nothing, right? We took array and we would just divide until bottom level I have arrays of size 1. And guess what? They're all sorted. Now we come with ℔ is running. You can still access it. So now we can start switching to conquer part. We did the divide. Now we switch to conquer and we start merging. But what we merge, we have array that is sorted, array that is sorted, and we merge two sorted arrays. So here we return from recursion. And as we go up, I basically on this level I compare 8 and 3, see which one is smaller, and decide how they, put them together in sorted order. When I come back here to this function, I have 3, 8, sorted array, and another sorted array, and now I will merge them. I will show you animation of how merge works.
Please to channel my
But this is a merge process. Okay, so take this exact merge together, and at the end I have half of my array sorted, half of my array sorted. I only just need to nicely put them together, and this is not very expensive operation. I will show you in a second how it's done. And we have it. Okay, let's talk about them. Yep.
Understand the middle part of 3, 8 to 6. What happens?
3, 8 to 6. Sorry, where?
Like the second live from middle. 3, 8 to 6. How does they live? Because
This
it's-
one?
Yeah.
Yeah, so here I have animation that shows how sorting works. We have two pointers that go and compare things. This array uses comparisons. Let me show you that, and if you have any questions, we'll come back to this one. Okay. So here I have a red array that is sorted. I have blue array that is sorted. And I took them of different sizes on purpose because sometimes you cannot nicely divide your input data in half, right? Maybe it's not divisible. You can have an array that is bigger than another one is smaller. How do you merge them together? So here, that's why my auxiliary array rests. I will be copying here items, and I will make sure that my purple array is sorted. Notice I have two pointers. They point at the beginning of each of those sorted arrays in my input. And I will be consistently comparing numbers pointed by the pointer. So first I compare 3 and 4. Okay, I have 3 and 4, and I just compare them. Which one is smaller? Well, 3 is smaller, so 3 gets copied to my purple array, and because it came from red, we will increment red pointer. And then we repeat. I compare now 6 with 4. Okay, I just only look at what pointers give me. 6 compared to 4. 4 is smaller, so 4 goes here. Because it came from blue array, I will increment now blue pointer. I will not touch the red one. Red one is still there. And I repeat. Now I compare 6 with 5. And 5 is smaller, so 5 goes here. It came from blue array. Blue pointer moves. If we have duplicates, then we can resolve it nicely. Just anyways, I'll talk about this in a second. 6 compared to 8. 6 is smaller. We put it in here. And iterate red pointer. Okay, let's do a couple more. 7 compared to 8. 7 is smaller. Put 7 here. Iterate red pointer. Now we have 9, 8. 8 smaller. Put it in. When we iterate blue pointer, it falls off the back of my blue array. It ended. So now it's easier for me. I can save some runtime on things because I can now, I don't need to compare anything anymore. I take the other pointer and simply walk and copy everything that is left to the back of the array, from the back of the red array to my purple one. So I copy 9, I copy 10, and so on. This operation is linear, right? It runs a linear number of operations. We can even count how many comparisons we did in the worst case. So I did here less comparisons because I kind of, one of my arrays ended soonish, and then I just was copying things. But say in the worst case, if you have total of n numbers here, if you have total of n numbers to sort, then in the worst case you will use n minus 1 comparisons. And that's O of n. Right? So a merge operation takes two arrays sorted and merges them in just by walking through them. It's a very efficient thing, and you cannot do better than that. Okay, so you know that running time for merge sort is n log n. It's a little bit tricky to to answer, to tell you the running time by analyzing those things, because I'll show you next slide. You don't need to memorize anything about this pseudocode. Just wanted to show you the logic behind merge operation. So here's merge of two things, and that's a lot of work here. But the running time is nice. And this is merge sort code where we have, we first divide. I have two recursive calls. They recurse on front of the array and back of the array. They're using indices to know what is the problem I'm recursing on. P and Q, those are starting and ending index. I'm not copying array anywhere. That's where copying is used. So I do copy things in merge operation because I need auxiliary space to put my stuff in when I work. Here I'm just given a pointer to array and just indices. So from here to here, that's your problem. I have a whole array, right? But for my recursive calls, I say only from here to here, that's your space. For another function, that's from here to there. And there are two recursive calls, and only after both of them are done, I do have a call for merge operation. I guess I want to go to this slide, because I want to show you how the control flow works here. So imagine I come and call my merge sort on this input array. And then it says, okay, we come here, and we come to the first recursive call. And that's where I go. I have merge sort on first half of my array. And in code for that, I also only come to the beginning and have a recursive call down further, and then here. This is from where I first return. So I will return from this function, and I will go execute next in line. And that's this one. Okay, so here I'm coming back from this function. When I'm coming back, here, that's my first call to merging operation. 8 and 3 being merged together. Okay, for example, this call didn't even happen yet. This call didn't even happen yet. It's kind of in the future. Okay, so when after merge is done for 3 and 8, here, maybe I'll take laser. My code here terminates for 3 and 8, and I go back. But where do I merge? I merge from this line. I merge from this line for this function. For this function, I merge at this line, and I have second recursive call. So I dive deep into 2.6, and then I go there. So notice we execute merge operation only when we're done with first recursive call and second recursive call. Means we already have this half part sorted and this part sorted. And then we just merge them together.
Alrighty.
Um,
The normal one. If it's
let me maybe.
not, did you say that? Like if it's
So in terms of size, let's first think about the size of my array. My array was a size n. I have two recursive calls, each of size n over 2. And then I have four recursive calls, each of an array of size n over 4, and so on and so on and so on. And if you think about this as a tree of, it's a recursion tree, you can say, wait a second, it looks like a recursion tree for M algorithms that we said is terrible, slow, and inefficient. Right? Let me show you for a second that algorithm. Here's M algorithm that is binary tree, same as merge sort, and we said it's exponential running time. And I go back to my merge sort and I show you exactly same tree. And I say, that's amazing, this is so fast. So what's the trick? What's the major difference between the two? Sorry, I'm looking at you because you always answer. I don't force you to answer. Yeah.
I don't know if this is right. Is it that each branch or whatever is different from all the other ones? So you're not repeating logic.
We're not repeating things, that's for sure, but we still, it looks like we have exponential number of calls. Is it exponential? What's so different about this tree compared to the previous one? How tall is this tree? How soon do we reach this situation where my array is of size 1? Yeah, we start with n, and then divided by 2, by 2, by 2, by 2, by 2. Yeah? Log n. Right? So we have log n levels. The previous tree had n levels. Remember the table when we compared n and log n? When n is billion, log n is just 30. So this tree is very short. It has only log n levels. It's really just a very tiny tree. It branches a lot, but it ends very soon. Yeah?
I have a question. What if the size of the array is
Yeah, you see, we're dealing with indices here. We are not, and there is a, floor. So we just take image, like with a median. Remember, we hit in the middle, but we might, offset slightly, right? And we can decide we want this smaller than that or that smaller than this. So we have things that are not necessarily of the same size, but if we get together, say 17 items, we have an auxiliary array of size 17, and we nicely put everything together. Yeah, it's designed to work on. Yep.
Could you explain how the indices are how it goes through the indices in each it's kind of confusing.
Yeah, it is. So the thing is, you don't need to know the pseudocode. I'm explaining logic mostly, but indices are indeed confusing because at the very first call it's from say 1 to n. Assume we're starting with 1 and not 0. But then here we hit in the middle, right? So 1 plus n over 2, we hit in the middle and save, and one recurses on 1 to this new number q, and the other one starts with q plus 1 here, q plus 1 to n. But every call now, every recursive call cannot operate with 1 and n anymore. I will use starting index for one, like I will have, that's why it has P and R. At the beginning, P is 1, R is N, but for later recursive calls, I just have to call them different things because they will be different. But the idea is the same. Whatever array given to me, imagine this is starting index P, this is ending index R, we find middle, P plus R over 2. We hit in the middle, and now we recurse on from P to Q, and then from Q plus 1 to R. That's the whole logic. Yeah. Okay.
Please do channel my
Sakrapara. There are only log n levels.
Sakrapara. Sacrifice.
If we to analyze the running time of our algorithm, then remember this. I should have it in my slide somewhere. Anyways, so running time of algorithm on input of size n. That's my function. I want to see what it is. So I have 2 recursive calls, each on same problem but on half the size. It means I have to think about this. What's the running time here? This is recursive call. It's the same problem, right? I have recursive call on the same, it's the same problem, but input got smaller. And then I have another one like that. So I can multiply this one by 2. And then we said in merge, I do that amount of work. So running time of my of merge sort can be expressed as 2 recursive calls. I don't know what this equals to yet, plus price that I'm paying for merging 2 things. This is known as recurrence relation and describes running time of merge sort. We don't solve them in our course. You usually do this in ComSort 804. There are different ways to solve those, but I want to give you intuition how to do this. Yeah? T is time, running time of algorithm, merge sort in my case, running time of my algorithm on input of size n. Remember when we talked about big O and big O notation, we had n axis here, and this one was still n. Running time. Or I express this equals to this. Because I cannot solve this, I need to solve this to get that, right? But I just don't know yet what this is. Let me give you intuition how to solve those things. I cannot solve it yet. You can use unfoldment to solve it, but I will use recursion tree to do that. So imagine the same tree, but now I want to document amount of work I do per each recursive call. So here I have merge operations. It merges 2 arrays of size n over 2. Together it cost me basically n operations, right? Let's call it n. Okay, at this level. Here at this particular spot, I do merge 2 quarters together. It is n over 2 operations. Same here. Okay, so imagine that every node is the amount of work I spent at this particular recursive call. And if you remember what we do, we only merge things. So first we divide. Imagine it's like no work at all, and then we start merging. Merge is the only actual thing we are doing here. Okay, I know that I have log n levels. So I have n operations per this level. How much work do I do at this level? So now look, this running time really sum of all the values of all the nodes. If I sum up all the values, all the work I do per every node, this will be a running time of my whole algorithm. And I will do it step by step. layer by layer. How much work do I do at this level? N, right? I do n work, n over 2 plus n over 2, n work. How much work do I do at this level? N, right? How much work do I do at this level? N over 8 times 8. There are 8 nodes like that. So n, 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 n. So at every level of my tree, I do n operations. And I have log n levels. So what's my running time? No, n times log n. That's where this running time comes from. Okay, so that's intuition. Okay, so not every recursive algorithm is slow. This one is amazing. It's super fast. Be careful with recursion. You not only need to stop it, but also not to make it too slow because of branching and stuff. And analysis usually difficult. It is nice intuitively you can see your tree like that, but for some problems it cannot be that nice. Sometimes an amount of work per level is not that nice. It can be a different number. Okay, thank you
Please do
everyone.
channel my
I will see you next week. We will talk about our last topic is relations. And if you are writing test today, good luck. I will see you soon. Okay, bye everyone.
Are you going to?
Thanks again.
Oh, are they supposed to do this? Yeah, it's a Thursday, the day before the Friday off. I did not know we have Friday off. Oh, next Friday? I thought it was like this. Early's $5 and then late's $5.
Please do channel my Sakrapara. Sakrapara. Sacrifice.
I think like they say like the dress code on the Let's make sure we never forget anything. Look on the Where are you getting picked up from? I said that right.
Would you ask the running time?
Have a good weekend.
What do you mean allowed?
Huh?
What do you mean allowed?
No, like it's not work.
Yeah? Or you go to south them and then keep walking straight and that's slope.
Oh, so it's easier.
Yes.
Okay, let me see if I know how to do that. Will I get lost?
Laggy time, that is true. Naimam Gedriana. Melissa Gedriana. Sophia Dene. I said that we're heading home. Even lunchtime can I own that kind of plan. Come on to free with that. Jeez, it's so cold. I can't with the weather. Look how deceiving it is.
That's nice.
It's cold. Sorry, Helen waiting for that. Oh, France, that's cool. බයික් එක පැමුණට රීන ගණන්ගල තියෙන සීතලයි. මට චැට් එක පේන්නේ අවුව නිසා. ස්ක්‍රීන් එක පේන්නේ පොඩ්ඩක්. කැමරාව මොකද්ද? කැමරාවෙන් මොකද්ද පේන්නේ කියලා මම දන්නේ. ඔහෙත් එහෙමයි කියන්නේ. අයන්නේ සීතලයි. Mm, 11 degrees, nice. මම එහෙනම් ලයිව් එක එන්ඩ් කරනවා. බයි බයි කට්ටිය. මම හිතන්නේ සිග්නල් කොහොමද කෝච්චිය දාලා යනනේ. good night ඔයාලට. ඉස්සරණයි බයි. සීතලයි.
Flip-flops with socks.
Is he going to class?
Bye. Ayo, bye. Good night. Everyone sad night. May pagtagal. Aduh, excited.